We will do this problem that will help us tie all of the things we have learned about equilibrium. Now, something you want to know is that Kc is small. This means that it will favor reactants. The problem says the reaction vessel initially contains 0.75 molar CO and 0.75 molar H2O with no products. Find the equilibrium concentrations of all species. This looks like a very difficult problem because we don't know the concentrations at equilibrium. We only know Kc. But here's how we're going to get the concentrations. It's called an ice table. You will want to start with your full balanced equation at the top, which in this case was given. Never forget to write the states of matter because in this chapter is extremely important. Okay? Now, I in the ice table represents initial. The C is for change, and E is for equilibrium. Okay. So we are given initial concentrations. So we will start by plugging that in. We have initial concentration of CO and H2O. Now, in this problem, we have to pay attention that H2O is a gas. So we will count this in the equilibrium constant. It says we have no products initially, so these are just 0. For this, we will need Q. Q is products over reactants, just like equilibrium. Let's plug in the values. As you can see, there's zeros at the numerator. So Q is 0. Now let's compare Q and Kc. Q is smaller than Kc because Q is 0 and Kc is 0.04. So in this case, the reaction will proceed forward. If the change is forward, this means that the concentrations of our reactants are changing by negative X, and our products will be changing by positive X. When you do these X's, you have to make sure you look at the coefficients. All of these have a coefficient of 1, which is why we only have single X's, but let's say this equation changed like this. Well, then we know that the change for products will be double, just like this. Okay, let's continue. If we have the initial and we know the change, we know that the equilibrium will be the same as this. Remember, this last row is for equilibrium concentrations. Now, we still don't know what the concentrations of all the species are at equilibrium, but we have Kc, which is the equilibrium constant, and we know that it's the same expression as this. Since we are given the Kc value, we will plug in all the concentrations. So here's what we have after plugging in all of the values. This looks like a little bit of a mess, but with rearranging, we can get it to look like a quadratic equation. This is essentially this, and we will now just solve for x. Usually, you will be needing the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. However, in this case, both top and bottom are squared, so we can just get the square root of the other side and solve. The square root of 0.04 is 0.2. We multiply both sides and we get 0.15 to x equals x. And we get that x equals 0.125. Okay, now we have just solved for x, not for the concentrations at equilibrium. But now let's just plug in and solve, because we already have where to plug in x. So because the concentrations of our product started off as 0, we know that x is the change and will be the concentration at equilibrium, basically, because right here is just x. Okay, so at equilibrium, the concentrations of H2 is 0.125 molar. The concentration of CO2 is 0.125 molar. And now for these, we will just solve. So 0.75 minus 0.125. The concentration of H2O is 0.625 molar, and the same thing for CO. So just like this, we have solved the problem, and we used an ice table for it. Something I want to quickly explain is the exception. You know how I said that normally we will be needing a quadratic formula to solve for x? Well, there's a small way around it, and it's a little bit like this. If the initial concentration over Kc is greater than 400, we are able to ignore the change, or the x, in the ice table. This is only for the specific concentration that we're plugging in, but it can help simplify an expression and help eliminate the excess so we don't have to use the quadratic formula. So in this case, we did have to use the quadratic formula, but let's double check. We have initials here, so we will plug in the initial concentration, and we have our Kc, which was 0.040. If we divide this, it is 0.75 over 0.04. This gives me 18.75. So this is why we can not ignore the x and why we had to use this. However, for understanding, let's pretend that this was 500. If this was 500, we can use our exception, which is called the 5% rule. If the exception applies, you are able to just cross out these x's. Remember, only for the concentrations that you use the initial for in here. But because CO and H2O have the same concentration, if we were able to use the exception, we would be able to cross out both. And this simplifies things a lot. However, in this case, this did not apply. But you always want to double check because it can make life a lot easier. And with that, we conclude this video about equilibrium. Now I know that it can be a little bit overwhelming, so I have made this cheat sheet, which I will post a printable copy of, which sums up everything and more of what I went over today. And it's just a good place to look for when you forget something, or you just need to review for an exam. This is what I used, and what will help you review. I hope you guys liked the video. Thank you.